Hello all, so we are going to start with modulator block diagram, and from this video we are going to start the communication entire playlist. So let's start. So here we have input analog waveform. As we all know that everything in nature is analog. So this is our analog input waveform. It is varying with respect to time, small t. This is our input. It will go into waveform encoder. So I am basically showing all the encoders which are there in our entire block diagram for communication system, especially our digital communication system. So first is waveform encoder. So what it will do, it will simply convert our analog input into a bits. That's it. So this is Shannon and everything, Shannon's algorithm. Then we have other algorithms as well, just to convert an analog input into a binary bits. Then after that we have channel encoder. So channel encoder, it is helpful for introducing the redundancy. And why this redundancy is useful? Redundancy into input bits. So this is useful for error correction and error detection, that we will see when we will discuss about the receiver part. So this is for error correction and of course detection. So we have Hamming code and everything. So all that is used for error correction and detection. And after that comes our modulator. So this lecture will be mainly focused in the study of modulator. And after modulator, this is our channel, or we can say the binary channel, right? Because our information is now binary, right? But this modulator will now convert this input bits, which is in the form of binary digits in 1 and 0s, into again analog input. So you might wonder that we have analog input here, and again we are converting this analog input here. So are we duplicating our efforts? Is it so? Right? So all this thing we will see in this lecture. So actually this analog signal and this analog signal both are different, and we will see this is our baseband analog signal. We will see the representation of baseband and passband as well. This is our baseband analog signal, and this signal has the capability, let me write, so this signal has the capability to travel along the channel. This we will also see in terms of mathematical equations, and this signal is not having that capability, so it cannot travel through the channel. It will vanish because it has low power. But of course the source which is generating this, right, if it is capable of traveling along the channel, then we don't need this, right? But fortunately in most of the cases we have to do this waveform coder, then channel encoding, and then modulator, right? So let's start with our modulator block diagram. So we are now going to zoom into this modulator block diagram in next page. So again I am taking, this is our modulator block diagram. Let me write, this is our modulator block diagram. So firstly we have our input bits. So as we saw that we have input as bits. So I am just writing any random bits. This is arbitrary. So this will convert these bits to samples, right? So what is sample? Sample is that we will convert each symbol, right? Each sample will be represented by some number of bits, and that bit is called sample, right? This will be converted into, just I am writing first, then I will explain. So just bear with me for a few minutes. So it's summation ak, then delta t minus kt. Now you might wonder what is this. So this is nothing but our, let me show you the previous page. So this signal, right, this signal is represented by this equation ak delta t minus kt. This bracket is not here. Okay, so it's ak, let me write again that it's summation k ak delta t minus kt. So what it suggests, what is ak here? Let me explain all the things. That ak is weights of our impulse, right? And it is decided by, these are the weights and are decided by, or we can say decided based on our input. based on our input like this, okay, our weights are decided. And so as you can see, this is a signal which is just shifted by t, right? Now what we do after this, we just pass it through a filter. Now what this filter will do, all this thing that we'll be seeing in our optimal filter, that is our match filter, okay, in our receiver part. So right now just we are passing it through one filter, and why we are doing this, that I will show you in a minute. And after that we are getting over here our baseband signal which is ready to transmit. This is our baseband analog signal. And it is summation k ak, and now it will be pt minus kt. It will be this, the impulse response of this filter. Now let me show you how I wrote this, right? And after that, this is baseband. We will be converting this baseband into passband as well. So just let me complete the block diagram, then we will show you the calculation. So from here, what we will do, we will multiply this signal with one complex exponential. So it is called rotating complex exponential. And when we multiply any signal with this rotating complex exponential, we will get our passband signal. So I am just denoting it by SP of t. We will see how we will get this passband, what is passband and baseband. Everything is this in this lecture only. So first of all, let's start step by step how we got this, right? So firstly we got the bits. I'm just repeating that firstly we have bits, then from bits we have our signal which is the combination of weighted impulse, and this weights will depend on this binary inputs, right? This weighted impulse is passed through a filter, and after filtering we will get our baseband signal which is ready to transmit. But this baseband signal will have some limitations that we will see, and that's why there is a need to convert this baseband signal into a passband signal, and we will convert this passband signal, the baseband signal from the passband signal using this complex rotating exponential, right? So let's start how to proceed. So here let's take some random pulses. So we have some random pulses. These are the bits, right? These weights are different, and these are decided by, these are actually AKs, right? All are AKs. So these are decided by the inputs. These are the pulses. So it is nothing but its summation AK, summation across all the Ks. AK, since these are pulses, this is delta t minus kt. Now when we convolve this, because when we pass through filter in time domain we convolve, this is the convolution operation, right? So when we convolve this, let's say, just I am assuming arbitrarily, the impulse response or the response of our filter pt is given by this shape. It's more or less like a Gaussian curve. So when we convolve this to, what we will get by the convolution property, we will be having this cap over here, we will be having entirely through all the pulses. So it's like this, all the cap will be here, right? So after that, if we draw this signal again, okay, here, then what we get is something like this after convolution operation, right? And this is our baseband analog signal. So let me show you that this baseband analog signal is being generalized by just multiplying this input with our filter response, and we are left with just we have P here, right? So let me show you the convolution property, how this works. So summation k across ak delta t minus kt, its convolution with pt. So as per the property of convolution, we will be having summation k from minus infinity to plus infinity ak, and we have p of t minus kt. So just whatever term is here, it will be reflected with p, right? So this is the property of convolution. So the same thing we applied and we got this. Now let's focus on passband to baseband conversion. So as I said, baseband signal is not good because it will vanish if we can just use baseband signal to travel across the channel, because there are some losses in the wires as well. So for that purpose we convert into passband. So as I said, in order to convert a baseband into passband, what we need is that we have to multiply. Let's say we have our baseband signal s of t. So if we multiply this signal with a complex exponential having frequency omega c, this is in obviously radian per second, then we will get our passband signal. Right? So how we will get this? So if we will see the Fourier transform property, then if let's say s of t has Fourier representation s of f in frequency domain. Sorry, let me write s of f. So if s of t has frequency domain representation given by s of f, then by the Fourier transform property, e raised to j omega t s of t will have Fourier representation. So this signal e power j and this will be having Fourier representation s of f minus fc. Right? So whatever frequency omega c will be there, so obviously we know that omega c will be given by 2 pi fc. So this fc is here, right? So as you can see that previously our s of t signal was baseband signal, so its frequency was, its center frequency to be exact, was somewhere around dc, that is frequency was 0. dc value has no frequency component, right? So it is frequency as 0, so it is somewhere centered around dc, right? But now as you can see that if we plot the pulse, then it is centered somewhere around fc, right? So we have non-zero frequency, and from Fourier transform symmetry property we have minus fc as well. This is just for analytical ease, for analytical easiness for calculation purposes. So that's why we use this fc, and now we will see that how this fc will be useful, right, in transforming the signal, from the transmitter side to the receiver side in next lecture. So I hope you enjoyed the video. Thank you.